8.1, basic integration techniques. So we're going to review some integration techniques that supposedly you saw in Calculus 1, but who knows? Maybe they ran out of time and didn't cover everything. But we'll go over this page, which has a bunch of stuff that some of the stuff you may not have seen, okay? But I claim that you definitely saw Technique 1 in Calc 1, or at least you better. Like if they ask you to integrate this thing, you can't integrate it right now, not even with U sub. It won't work. U sub won't work. Instead, you're supposed to FOIL it out. You guys know about FOIL, expand and multiply. And then once you FOIL it out, it's pretty easy to integrate. No U sub required. Okay, no U sub needed. You just need to multiply it out. Okay, I'm not going to do that problem. Just going over quickly how you would attack an integration problem. And students that are good at integration are the ones that are good at pattern recognition and who have practiced a lot. So what if somebody said, hey, integrate this mess right here? Oh my God, are you kidding me? That you don't want to try to integrate right now. Instead, you separate the numerator. What I call this the split up trick, although it's not really a trick. Although my Math 45 students think it's a split up trick. But basically it says if you've got a fraction, it's legal to split it up into two separate fractions, if it helps. Now, once you split it up and you are asked to integrate these two guys, this first term is going to require the log rule with U substitution. And the second term is not the log rule, something else. Does anybody want to guess at which rule of integration that second term would need?
Arctan.
Very good. Right on, Jasmine. Arctan rule. Right on. Okay. Complete the square. We did some of that in the inverse trig integration module. If somebody says, hey, integrate this, you can't. But if you rewrite it where this is rewritten equivalently, that's the same, it's equivalent, then you can use the arc sine rule for this particular problem. There's other complete the squares where it's not the arc sine rule, it's something else. What about this beast? This is called an improper rational function. A rational function is basically a polynomial divided by a polynomial. An improper rational function is where the degree of the numerator polynomial is greater than or equal to the degree of the denominator. And if that's the case, you have to do what we call polynomial long division. And yes, that's going to be like, I know some people last semester, some people like, I haven't done polynomial long division since algebra. And it's like, yeah, well, welcome back. And yes, that's going to be on the midterm on Monday. Know how to do it. I guarantee you it's going to be on the midterm. Like I'm telling you right now, one of the problems that will be on the midterm, polynomial long division. Yay. Know how to do it. And now this one is I claim this one's rare when it works. I rarely use it because it's so rare, but it does work when it does work. And then when it doesn't, it doesn't. But this is not doable whether you even try doing it via, log rule or arctan rule. But if you add 6 and subtract 6, which is basically just adding 0, so you're not doing anything illegal, and then use the split up trick, this guy right here, the log rule will work, and then this guy right here, the power rule will work. So that's one technique. This one is, and I kind of even hesitate to put this in this section here, but there are sometimes when trig identities will be used, and they can be helpful. This one, which is a nice trig identity you probably learned in trig, which I call the power reduction formula. I actually promise that I won't give you anything requiring the power reduction formula until section 8.3, because that's when we're really going to use it, okay? Not that there's not going to be any other trig identities, don't worry. And then finally, multiply and divide by a special version of 1. So if somebody asked you to integrate this beast, it's not integrable. But if you multiply by a special version of 1, this is the same as 1, that involves what we call the Pythagorean conjugate. The conjugate of 1 plus cos is 1 minus cos. It turns out after you use the split up trick on this, that it will be integrable and then you can work on it. Another way to use the special version of 1 is this guy right here, where when you multiply by the special version of 1, this now is doable because you can use the log rule on it, okay? Some trig identities that you should know are tan squared theta. Like if somebody said, hey, integrate tan squared, you'd be like, oh man, no way, there's no integration rule for that. Then what you would do, the trick is, oh, but that's the same as sec squared minus 1. And now it's integrable because the integral of sec squared is, I don't know if anybody knows. Does anybody know the integral of sec squared? Off the top of your head, say. Maybe not. It's okay if you don't. It turns out it's tan. And then the integral of 1 would just be theta. Okay, so this one we did need a little trig identity. And, you know, it's always good to know that sine squared theta plus cos squared theta equals 1. That's always a good identity to keep handy because it can come up. Okay, now let's start. So this first page of actual examples, what I like about it is you have to be good at pattern recognition to be a good integration student, because the first 3 examples here almost look like they're the same integral. If you look at A, B, and C here for problem 1, there's just slight changes, but they lead to very different techniques. So let's do them in turn. So the first one I claim requires the arctan rule. So in case you forgot the arctan rule, it looks like this. du over u squared plus a squared is equal to 1 over a arctan u over a plus c. You got to know that. And by the way, this formula is not in Briggs. We went over this, so I want you to know it from my class. So in this case, and this 4 is just a constant multiple, if I rewrite it as a difference of squares, it might be easier to see that it is really the arctan rule. So you need to identify your u, your du, and your a to get full credit on one of my exams. And then u is what? Anybody want to guess?
X.
Mm-hmm. Good. And then so what's du?
Dx.
Mm-hmm. And then a?
3.
Yep. So there's really not much to do in this problem, but don't forget your 4. That's part of it. And then 4 times 1 over a. And then sometimes my math lab prefers when you do tan inverse instead of arctan. I don't know why. And we're done. Okay. Arctan rule. How about letter B? Is that arctan rule? It's not the same.
Log.
Log rule is correct. So know the difference. Well, how do you tell the difference? Well, you can tell the difference because a portion of the derivative of the denominator shows up in the numerator, because here you have 1 over u du is equal to ln absolute value of u plus c. There's your log rule in action. This 4 you can pull out in front. And so if you identify your u and your du here for the log rule, the denominator is the u, and then a derivative of x squared plus 9 is 2x dx. And so it turns out I need a 2, and I have a 4 out in front, but I'm allowed to put a 2 in, provided I divide it out. That's how I do this kind of u sub. And then now when I rewrite this in terms of u's, this is just a 2, and now it looks like 1 over u du for the integral. So then I have my 2 ln of u plus c with absolute value around the u. And then here I get my final answer. Now, for this problem, not for all logarithmic problems, it is totally legal for me to replace the absolute value notation with parentheses. Why are both okay for this problem? Anybody want to guess why this particular problem, it's okay, but not all the time?
It's not possible for it to be negative.
Very good. Yeah, x squared plus 9, no matter what x you plug in, you're guaranteed for it to be positive, so you don't need the bars. It's redundant. But if you have them, don't worry, it's okay. So there's your answers, and we're done with part B. Now, what about C? Wow. That's nuts, isn't it?
Long division.
Long division is good. This is an improper rational function right here. It's a polynomial divided by a polynomial where the degree of the numerator is equal to the degree of the denominator. And that's what makes it an improper rational function. So yeah, polynomial long division. Oh no. So before I do this problem, I want to start with a basic division problem, just so you kind of get the flavor. So what if I said divide 25 by 6? Let's do some vocabulary. This is what we call the dividend. This is the divisor. So if you did a little division problem on the side, you go, okay, 6 goes into 25 how many times? 4, right? And then 4 times 6 is 24. So you put that product down underneath and then you subtract and then you get a 1. Are we done? Yes, we're done because this remainder is less than the divisor. So the remainder, I like to call big R, big R. And this is your quotient, which I like to call big Q. And this is your divisor, which I call big D. So what happens? You need to put your answer as Q plus remainder over divisor, quotient plus remainder over divisor. So would you agree that 25 divided by 6 is equal to 4 plus 1/6?
Yes.
It is. That's true. It's good. So the reason why I wanted to do this is to make sure that you have your polynomial long division idea correct. So, and you may laugh, but I've seen students who set up their problems backwards, and it's not pretty. So for example, let's see if I'm trying to erase here, and my erase tool is kind of slow. If I were to set up this polynomial long division problem, whoops, which one would be the correct way to go? Oh boy. What just happened? All right. So would I go like this? X squared plus 9 goes into 4x squared. Or should I say that 4x squared goes into x squared plus 9? Which one of those is the correct setup?
The second way.
The first one.
Oh, the first one.
So like, you know, when we did 25 divided by 6, we said 6 goes into 25 and not 25 goes into 6. Hello?
Yeah. So
This
it's the first one?
This is a common student mistake. And they think, oh, well, I would never do, 25 goes into 6. Well, yeah, you would if you pick the wrong polynomial long division setup here. Sorry. So which one of those, the first one or the second one, is correct?
It's the first one.
It's the first one. This one is not good. Okay, it's not correct for this particular problem. Now what? When you're doing polynomial long division, you only need to focus your eyeballs on the highest power terms. So the highest power term for the divisor is just the x squared. For the dividend, well, he only has one term, so it's 4x squared. So this is how you tackle it. X squared times question mark will equal 4x squared. So what should I put in place of the question mark?
4.
Yes. So you're starting your quotient up top. And then you multiply that quotient with the entire divisor. 4 times x squared plus 9 is 4x squared plus 36. And then you subtract. You have to be careful because this negative needs to distribute essentially, because 4x squared minus 4x squared is 0. And then you have a 0 for a constant term. 0 take away 36 is minus 36. Am I done with my long division or should I keep going?
You're done?
I'm done. Why? Well, because this is a polynomial, by the way, negative 36. It's a polynomial of degree 0. What do you mean? That's kind of weird. Well, you can think of it as having an x factor raised to the 0, because so it is a polynomial. So then what? You've got your Q, your quotient, you have your R, your remainder, you have your D, your divisor. Remember, you're going to rewrite it as Q plus R over D. And if you don't, I'm going to take away a whole truckload of points. So then what? For this problem, you're going to go 4 plus negative 36 over x squared plus 9. And you're going to integrate that instead of the original problem, because you can't integrate that improper rational function. So now what? Good news, the integral of 4 is easy peasy. With respect to x, it's just 4x. Plus, how am I going to integrate this? Well, I'll pull the negative 36 out. This should look familiar to you. How do we integrate this guy?
Arctangent.
Yep, arctan rule, beautiful. So you need to tell me the u, the du, and the a to get full credit. So for this one, u is x, du is just 1 dx, and a is 3. And so you'll still have this 4x, you'll still have the negative 36, you'll have 1 over a, 1 over 3, arctan of u over a plus c. And then of course I like you to reduce. So what does negative 36 over 3 reduce to?
-12.
Negative 12, right? Mm-hmm. Oh, that didn't work too well. Wow. Yep. So I'll have plus a negative 12 here. Okay. And I'm done with this problem. Any questions so far? So on this next page are a whole bunch of other problems that, good God. I claim that I purposely put in some problems in here that cannot be evaluated by us yet until we cover something else in chapter 8. Okay, so that's going to be sort of the trick here. Can we spot which ones are not doable? Okay, let's start off with letter A. I claim letter A is doable. What rule of integration are you going to use to integrate that guy? Anybody have a guess? Educated guess? Log rule is right, Brian. What's your u then? Tell me.
ln x.
Good. And then what's your du?
1 over x.
Yeah, dx, right? But 1 over x dx is already in the integrand. Good news. It's already there. It's like we're in luck. So we already have the 1 over u du ready to go. So the final answer is going to be ln of absolute value of u plus c, and then you just need to back substitute. So, but is this right? Can you take a logarithm of a logarithm? That looks kind of weird, doesn't it? Is that legit? Yes? No?
No.
Okay, why would that not be okay? Well, let's whip out a calculator. I'm just curious. Like, could I take ln of 2, for example? Would the calculator let me do it? Or ln of 10?
Yeah, I don't do it.
I mean, if it's not legal, you'll see an error on your calculator. It'll get very unhappy with you when you try to, punch in a number. Like try doing ln of negative 2, okay? You'll see real quick that that's not okay. Ignore what I got here. It's got a toleration problem. Like if I go ln of 2, I think everybody would agree that's fine. If I go ln of negative 2, what happens? Oh, error, non-real answers. Oh, that sucks. Okay, what about ln of 2? I don't know. Let's just find out what happens when we do it. It could be weird. I don't know. No, it was okay. So it's totally okay to take an ln of an ln. It's legit. So in other words, this is an okay answer. This is totally okay. You can take a logarithm of a logarithm. Okay, so I'm done with letter A. Let's move on. This one looks pretty weird, and I'm going to need to use the split up trick on it, even though it's not a trick. It's just basic math. So I'll have 1 over x minus x squared ln x over x. And then, of course, you want to reduce if possible. And I claim that the second term you can reduce just a little bit because x and x squared have something in common, right? So really, I'm integrating 1 over x minus x ln x dx. And this is doable. This antiderivative is ln of absolute value of x. But what about this thing? We can't do yet. And I say yet because after Friday's lecture, you will be able to do it. You need IBP, integration by parts. And you guys don't know that yet, technically. So I'll save that for later, okay? Let's move on to the next problem. Letter C. Can we do this one? Or would this need future concept?
Is it log rule?
Well, if we did log rule, it would have to have this 1 over u du look. So what would be your u if we tried using the log rule?
Is it power rule?
Mm-hmm. Power rule. So you guys just took a quiz for me that was due this morning, right?
Yes.
Say yes. I claim that the quiz 3 had this problem on there. Do you remember? Or something like that might have been squared.
Yeah.
Say yes. Or maybe you don't remember. I claim both of these are the power rule. Both would require the power rule. So I claim this is actually, both of these are calculus 1 problems. If you didn't get it right, pay attention right now because you should know this already. You're calculus 1 grads and you're supposed to know how to do calculus 1 type integrals. That's part of the deal. Yeah. You know, and I know that that quiz was pretty challenging because a lot of the differential equations on there, once you separated the variables, the integration was pretty straightforward, or should be, if you're a Calc 1 grad. So let's do the letter C first. If you let u be ln x, then du is 1 over x dx, which is already in the integrand. It's like, yay. So when I rewrite that in terms of u's, I just have u du. And then the integral of that is u squared over 2 plus c. And then I'll put my u back in, and then that's just the ln of x getting squared divided by 2 plus c, and I'm done. Now the quiz problem is, well, it'll have a slightly different answer, but it has the same strategy. You're going to let u be just ln x, and du is 1 over x dx, which is already there in the integrand waiting to get swallowed up by the du. So now this looks like u squared du. But using the power rule on that, you get u cubed over 3. So that's just going to be the ln x cubed over 3 plus c. So on your quiz, should have been pretty straightforward. Any questions on this?
Professor?
Yeah.
For the quiz problem, it kind of confused me because it was ln 3x squared, I think.
Yeah, that's excuse me, slightly different, but not much because Sabri, take a look here. Oh, wow. Remind yourself to never buy a Microsoft Surface Pro, okay? They're like the worst. You square this. Are you with me, Sabri?
Yes.
Good. So watch closely how I roll. The derivative of ln of 3x is 1 over 3x, and then using the chain rule times the derivative of 3x, which is what? You tell me, Sabri. What's the derivative of 3x?
Oh, x squared, or 2/3 x². Oh, I think I did the integral, sorry.
I'm just asking you to, what's the derivative of this, my dear? I'm just asking you a little piece of the problem, okay? What's the derivative of just 3x?
3.
Thank you. So I'm using the chain rule here, all right? But then dx, these 3's cancel, so the du for the problem is just 1/x dx, because the 3's cancel. Is that clear?
Yes.
So good news, Sabri, because 1/x dx is already in the integrand waiting to get swallowed up as part of the du. So this problem is still looking like u squared du. And if you want to continue on that, please come to office hours. We could talk about it some more, okay?
Okay, thank you.
You're welcome. So finally, letter D, what do we do to letter D? And I claim we can't do it yet. You're going to also need integration by parts to go do that. You cannot take the integral of ln of x. Please do not tell me, oh, it's 1/x. Why is that not true? Why is the integral of ln of x not equal to 1/x? What would you tell the student who said, yes, it is, yes, it is? You would tell them they're doing what?
That's the derivative.
That's the derivative of ln of x. Thank you. Thank you so much. Yeah, this is the derivative of ln of x, but it ain't the integral. They did not teach you how to integrate ln of x when you took calculus 1, believe it or not. I know, right? They actually, that was a big missing, but they didn't tell you that because they didn't want to. Shh, they were keeping it a secret. They thought you wouldn't notice. They told you how to take the derivative of ln of x, but never the integral. That's because you had to wait till this class. Congratulations, we're almost there. Stick around and you'll learn how to do that later this week. Okay, so moral of story, this last page we just did, some of those integrals kind of look similar to each other, but they require different techniques of integration. Okay, so now let's do the next page. Oh yeah, we got more fun and games here. Yeah. So I'm going to do number 3, and then I'm going to do part of number 4, and then I'm going to have you try and finish number 4. Okay, so let's look at these strategies. What's the strategy to do this problem? This looks really hard because it looks like a hot mess. It's like, I don't know, that's crazy. And the strategy is split up trick, or excuse me, not the split up trick. Sorry, my bad. I was looking somewhere else. Cosine rule. I used to have this be a harder problem. That's why, my old notes. Cosine rule. What do you mean? What's a cosine rule? A cos of u du is equal to sine of u plus c. Well, I don't know. That looks like it's cosine u with some junk in the denominator. Well, hold on a minute. If I let u be e to the negative 2x, what is the derivative of e to the negative 2x? You guys took Calc 1, you're Calc 1 grads. How do you take a derivative of this exponential?
U prime times e to the u.
Good. So that would be, what is your u though? Because we got a lot of u's running around here now that we're saying u is e to the negative 2x. What is the derivative?
Minus 2 times e to the negative 2x. Yes.
Thanks, Alexa. So would you agree that if I rewrote this with positive exponents, it looks like that? They're the same?
Yes.
Yes.
So what's the good news and what's the bad news? The good news is dx divided by e to the 2x is in the integrand waiting for us to serve the role of the du. But I'm missing, or I need, a factor of negative 2. But that's easy. I could put one in, provided I multiply the front of the integral by its reciprocal. So now I claim this integral, if I rewrite it with the intermediate step, looks like -1/2 cos u du. Yay! And so this is going to be -1/2 sine u plus c, and then you put your u back in, which we said was e to the -2x. And we're done with this problem. Yay. And there's your final answer. Questions? It's a tough one. Okay, I'm going to start number 4, and then I'll have you finish it out. Okay? So the strategy here is you're going to do that rare one I told you about, the one that's like, although truthfully, I would do this in a completely different way using change of variables, but I'm not going to tell you that yet. We'll do that one a little bit later in the section. You're going to add and subtract terms in the numerator, which is totally legal as long as you're not doing, anything, you're just adding a 0 essentially. Well, what am I going to add in this numerator that's going to make it work? Well, I'm going to add a 2 and subtract a 2, which means I'm not changing it. I'm just adding a 0. So that's adding and subtracting terms in the numerator. Ugh. Then you use the split up trick. Not really a trick, but you know what I mean. Split the fraction into 2 fractions. So what do I mean? You're going to have the 2x plus 2 all over x squared plus 2x plus 1, plus the other guy here, the -2 all over x squared plus 2x plus 1. You're going to integrate these separately, okay? So I'm going to put you and a buddy are going to work on the rest of this problem, okay? I'm not going to tell you how to do this one, but I claim this is a Calc 1 problem. That's a big hint. And for this second one, which is a little tricky, the hint I'm going to give to you is factor the numerator first, and then you might see what needs to happen after that. It's still a Calc 1 problem. Both of these are Calc 1 integration problems, okay? But you and a buddy are going to finish these two out so you get your final answer, okay? So this will be kind of fun here. Let's see, I'll do 14 breakout rooms. So one room will have 3 people in it instead of just 2. Okay, when I open up the rooms, I'm going to ask you a favor. You're going to go into the room and please turn your mic on so you can talk to your buddies. Try to work on these together. Sometimes 2 or 3 heads are better than 1, especially if you're stuck. Ask questions of your buddy. All right, when I put you in there, I'll come swinging around and check up on you to see if you're stuck. Bye. Okay, did you guys finish?
Yes.
Yes.
Okay, you think you got something that, looked like it would work? Maybe? All right, sometimes I wonder. Let's see here. So if I go back, let me do a share screen here real quick. All right. Okay, so back to this. What rule of integration did you use for this very first integral right here?
Log rule.
Log.
Log rule is correct. So with the u substitution happening, who is your u and your du?
The u, it's x squared plus 2x plus 1.
Mm-hmm. And du?
2x plus 2.
Mm-hmm.
dx.
Mm-hmm. And good news, that's already in the integrand. So this integrand is already looking like the 1 over u du that we need. And so your answer is going to be ln absolute value of u plus c. And then you can put your u back in there. And then you can get ln. And I claim that you don't have to put absolute value because it turns out that x squared plus 2x plus 1 is always going to be positive. You're guaranteed. Now, how about this second? I'll put plus c for now, but we're going to have another c. How about this second guy? Did you take my hint when you factored the denominator? How do you factor x squared plus 2x plus 1? What does the factorization end up being?
X
X
plus
plus 1
squared.
square.
X plus 1 times itself, which is just x plus 1, the quantity squared. And the reason why that was kind of cool is you really only have to worry about integrating this -2 over x plus 1, the quantity squared. Yeah. And then what rule of integration is going to get in the mix here to finish this problem out, this integral?
Power rule?
Power rule.
Power rule. So who's your u and who's your du for this power rule?
X plus 1 and dx.
1 dx. So this -2 is just a constant multiple, so it's legal to pull it out in front. So in terms of u's, the intermediate step here looks like the integral of 1 over u squared du. And if I rewrite that as u to the -2 du, we can use our power rule. Yeah. U to the -1 divide out by -1 plus c. Please rewrite this, cleaning it up with no negative exponents. So this will be +2 over u plus c, but then you can put your u back in, which was x plus 1. So your final answer for this problem, you got to put it all together because there were kind of like two integrals. You got to do your big old answer. You're going to have ln x squared plus 2x plus 1 plus 2 over x plus 1 plus c. There is one other answer, or two other answers I would be okay with. So what's another answer that I would be okay with? Well, because we factored this polynomial, you could have rewritten the log's argument as x plus 1, the quantity squared. That would have been legal. And if you really just want to be cute, I mean, I don't really care. But you could have said, well, that's the same as 2 ln x plus 1 plus 2 over x plus 1 plus c. All three of these are equivalent, and all three are fine with me. Did anybody get something different?
Is it okay if for the first integral we put log natural of x squared plus 2x plus 1?
Yeah, that's what I have right
Okay.
here. Yeah.
Oh, okay, sorry.
Yeah, that's totally okay with me. Okay, so hopefully you got a little bit of, good stuff with that, right? All right, so number 5. I claim that you had a problem like number 5 on your quiz, didn't you?
Yes.
Yes.
If you don't remember, you weren't paying attention to your quiz 3. You did that on the quiz, okay? And you need to complete the square because that's what was required of you in this problem. And I did something almost exactly like this problem in lecture when we did 7.7 on inverse trig functions and integration. I did a complete the square problem. So let me get a fresh page here. But if you're doing this problem using the complete the square, because you can't do it right now. Don't go, oh, I'll use log rule on this. It won't work. It won't work. You'll get stuck because you don't have all the ingredients that's required for you to do like a log rule or anything like that right now. So please mute yourself also, because I hear some people kind of, I can hear you eating breakfast out there. So you can't do this integral in any other way. So you're stuck. So the scratch over here on the side, let's just look at this polynomial here. Is there a way to complete the square? What I do before I start doing anything is I just rewrite the expression where I leave some space. I leave some space and I group the x terms sort of right next to each other, and then I leave some room, and then I put the constant term kind of over to the side by itself. So the idea with complete the square is you're going to add and subtract the same terms in the whole sentence. You can't, just add a term and then call it. You have to add and subtract, because you're essentially adding a 0 into the expression, which is legal, because you need an equivalent expression. So the question is, though, what is that special term we're going to add into the mix? And I always use my complete the square formula. It's always b over 2 squared, where b is the middle coefficient of the trinomial. So here, the number we're going to add and subtract is 2 over 2 squared, but that's 1 squared, which is 1. So that's what we're going to add and subtract here. Well, how is that going to help us? Well, it's going to help us because we're going to create a perfect square trinomial that factors nicely. Factors as something squared. So this is now what we call a perfect square trinomial. That's why we were doing this complete the square. I claim it factors as something squared. What?
X plus 1.
Yeah, this one's not too hard. Now this guy over here is plus 4, and I'm just going to make that look like something squared for a reason. You'll see in a moment why. We can rewrite 4 as 2 squared. And I'm done with the scratch. So I'm going to replace this denominator with its equivalent, which looks prettier. It's going to be more helpful for me to do the integration. Why? What rule of integration can I use right now?
Arctangent.
Yep. You got it. So that means you need to tell me the u, the du, and the a. So who's u for this arctan rule?
X plus
X
1.
plus 1.
Good. And then who's the du?
1 dx.
Yeah.
Dx and A is 2.
Mm-hmm. That's true. All true. So you have all your ingredients, so you're ready to go. Final answer is 1 over a. That's 1 over 2 for us, arctan. And the argument here will be u over a. And then plus c. And we're done with that problem. Woo! So that's the complete the square strategy. A good one. Really good. Questions? Okay, so the strategy was complete the square. Okay, number 6. What do you think? This is a polynomial divided by a polynomial, which means it's a rational function for an integrand. Is it improper? So my question to you is the degree of the numerator polynomial greater than or equal to the degree of the denominator? If yes, it's improper. So yes or no?
Yes.
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 It's improper.
Polynomial long division.
Yes, that means polynomial long division, baby. Somebody is awake and alive and filled with energy. Woo! Give that man a free Corvette. No, polynomial long division, you bet. Again, oh yeah, again. So there's your strategy, polynomial long division. You can't integrate without it. I've had students see me after class. Well, there must be another way to do that problem, right, professor? Like there's a secret, easier way, right? And I'm like, no, there's no secret. I'm giving you the easiest way. There's no way out. Well, I can do that without polynomial long division, I bet. No, you can't. No, you can't. There's no other way. If there were, I would tell you, trust me. I would want the easier way myself, but there is no way. So here you go. How many times does x plus 4 go into x squared plus 2x? This is a little bit trickier than the one we did earlier today, a little bit more involved. So let's keep our eyeballs on just the highest power terms only for each of these two polynomials, the divisor, which is here, and the dividend, x squared plus 2x. Okay, so keeping our eyeballs on the highest power terms only, x times what would give me x squared?
X.
X. So you start your quotient up there, you put an x, you're like, okay, x times x is x squared. And then you multiply that quotient with the entire divisor. So x times x is x squared, x times 4 is 4x, and then you're going to subtract. And don't forget to distribute that negative. So x squared minus x squared is 0. I won't bother writing anything down. 2x minus the 4x is negative 2x. Am I done? Or do I have to
No.
keep going?
No.
You got to keep going because this cannot be a remainder because this polynomial is of degree 1 and so is the divisor, and you're not done until the remainder is of less degree. So you got to keep going. Oh, well. So again, keep your eyeballs on the highest power terms only. What do I need to multiply this x by to give me negative 2x?
-2.
Good. Negative 2. So you're going to put a minus 2 up here. There's the rest of your quotient. And then you're going to multiply negative 2 with this entire divisor. Negative 2 times x is negative 2x. Negative 2 times positive 4 is negative 8. Draw a line, subtract, but don't forget to distribute that subtraction. So you're going to go negative 2x minus negative 2x. Well, that's 0. And you can pretend there's a 0 placeholder there. 0 minus a minus 8. What's 0 minus minus 8?
Positive 8.
Plus.
Positive 8.
Yep.
And this is the remainder. That's your R. This is your Q, your quotient. This is your divisor. So when you write your result, please remember that it has to be Q plus R over D. Don't mess that up because you don't want to do all this polynomial long division, which I'll give you like a point or two for partial credit. So then when we write our Q, we got x minus 2 plus R, that's 8, the remainder all over the divisor dx. And now I think we can integrate pretty easily. So the integral of x is x squared over 2. And then the integral of minus 2 is minus 2x. Plus, how do we integrate this beast?
Log.
Log rule. Oh yeah. U is what?
X plus 4.
Huh? And du?
Dx.
So we don't have to worry about anything. And so this is, if I pull the 8 out, it looks like 8 times integral of 1 over u du. So that's going to be 8 ln u. And then when you put your u back in, which we have is x plus 4, so we'll have ln absolute value of x plus 4 plus c. And there is your final answer for number 6. So the recap on that is polynomial long division.
Do we need
Rewrite
to put
in-
in 2 and 1
I'm sorry?
for the limits?
Yeah, it's a
Oh,
definite.
wait, this was a definite integral. Oh my God, David is awake and I'm not. Thanks, David. Yeah, I'm not done. Why am I not done? Does everybody see that I can't just stop? I can't do a plus C. I got to keep going. Oh man, really? Yeah. Okay. So what does that mean? I have to take this big mess and evaluate it at the limits. Ah, That's terrible. So the limits are 1 to 2. Keep going. So I put in the upper limit first. So I'll have 2 squared over 2 minus 2 times 2 plus 8 ln absolute value of 2 plus 4, whatever that is, big ugly number, minus, and then I'll evaluate at the lower limit, 1 squared over 2 minus 2 times 1 plus 8 ln absolute value of 1 plus 4. Oh God, this is a nightmare. Clean this up. So this is 4 over 2, which reduces to 2, minus 2 times 2 is 4, plus 8 ln of 6. And then minus, what do we have here? We have a half minus 2 plus 8 ln of 1 plus 4 is 5. So I'm going to distribute this negative here. So, and then let's see what we got here. What's this? 2 minus 4. Yeah, negative 2 plus 8. I think that's 6. No, excuse me. I can't do that. That 8 is not a, sorry. That 8 is a multiple. My bad. 2 minus 4. What am I doing? That's negative 2 plus, this is just 8 ln 6. That's just some yucky number. Minus a half, minus 2 is plus 2, minus 8 ln 5 after I distribute the negative. Try to clean this mess up. Negative 2 plus 2, that adds up to 0. Cool beans. So I just have negative a half plus 8 ln 6 minus 8 ln 5. That is the answer. We could go 2 extra steps here. Watch closely because I'm going to use some log properties, which you should know. If I factor out the 8, because that's a common factor between those last 2 log terms, and then I condense this difference of logs into one big old log, that's legal. You learned that in algebra. I have ln of 6/5. So that works. That's a perfectly okay. So this is an okay answer. This is okay. And if you want to even impress me some more, you can take that 8 and make it a power for the 6/5 quotient. So this is also okay. So we have 3 different answers. They're all equivalent and they're all okay. Awesome sauce. Okay, any questions on that one? Boy, that was kind of a nightmare, wasn't it? Okay, so I'm backing up here. This is the one I told you about that you may want to do a trig identity. So I'm going to put the strategy here as trig identity. Can't do tangent squared 2x. Well, why not? Can't do it. Well, what are you going to do instead? The strategy is the trig identity you're going to use is sec squared theta is, or excuse me, tan squared. I should do tan squared. Is tan squared theta is equal to sec squared theta minus 1. So what you'll do is you'll replace this tan squared with the trig identity equivalent, which is sec squared 2x minus 1, and you'll integrate that instead. Why? Because sec squared is integrable, but tan squared isn't. So just a reminder that sec squared u du is equal to tangent of u. That's the rule we're going to use, in case you forgot that. They should have taught you that in Calc 1. But, you know, they taught you a lot of stuff in Calc 1. Maybe you forgot some. I don't know. The minus 1, you don't need u sub for that. That's the antiderivative of minus 1 is just, you know, minus x. Well, okay, fine. But what about this secant squared 2x? The u is 2x. And then the derivative, the du for 2x is 2 dx. Now, here's what I want to show you, a common student error that just gets me. They'll go like this. Oh, we'll put a 1/2, you know, we'll put a 2 in and we'll put a 1/2 out in front and we're good. Yeah, but that's wrong. You have to be careful because this minus 1, he doesn't deserve to get hit with the half. Like, you don't want to do that to him. He's not the guy that needs the half. Only the sec squared does. So you have to be very careful you don't distribute that 1/2 into your final answer because you're going to blow. So what I would do is I would rewrite this where you'd split it up into 2 separate integrals, and that way you wouldn't be in danger of having this 1/2 hit both of those terms. So once again, this -1 out here, do that separately. So his integral is just the minus x, and then of course plus c. And now this sec squared, if I do the intermediate step, it's looking like 1/2 sec squared u du, which would give you 1/2 tangent u, and then you still have this minus x plus c going on, and then you'd finish it out by back substituting for u with your 2x. So your final answer for this guy is 1/2 tangent 2x minus x plus c. Questions? Okay, let's take a poll. Okay, take a poll. Got 2 questions up here for you. One is, how long does it take you to think of a brilliant reply? And then the second problem is, what is the age of your very first memory? 1, 2, 3, 4, 5, 6, 7. No idea. I thought you said this would be easy. Okay, answer these 2 questions. This is how I take roll. I know, right? Okay, and polling. Let's share the results with you. Okay, for problem 1, it looks like a lot of you straight away, I'm not buying it. I doubt that's true. I usually take a week. Okay, what's the age of your first memory? 2, 3? Yeah, I think I might remember 4 or 5. Nobody has their first memory at 6. A lot of people said no idea. Wow, interesting. Okay, thanks for voting. Okay, so number 8, we're just going to keep going here. I got plenty to do. How do we even tackle number 8? Like, what's the strategy for that? What's our strategy? Can you use U sub right off the bat with the power rule? What do you guys think?
No.
We'll do foil.
Foil out.
Foil, yes. Whoever said foil is absolutely right. Yes, multiply it out. Yeah, expand and multiply, also known as foil. Expand and multiply. Foil it out. Otherwise, you can't do it. Like, don't even try to do it without foiling, okay, people? It is not going to work. So you're going to go, what's 1 plus e to the x times 1 plus e to the x, like that. You know, first, outer, inner, last. So you do your FOIL. So your firsts, 1 times 1 is 1. Your outer is 1 times e to the x, that's e to the x. Your insides are e to the x times 1. And your lasts are e to the x times e to the x, which is what? E to the what? What's e to the x times e to the x, people?
E to the 2x.
Good. And then you want to add your like terms just to make it easier on yourself. 1 apple plus 1 apple is 2 apples. So this is a pretty easy integration problem now because you did this in Calc 1. This is going to require the exponential rule with u sub, where u is 2x and du is 2dx. But you don't want to put the 1/2 way out here in front. That would be wrong, because these first 2 terms don't need u sub, so they don't need the 1/2. So you should do that last term separate, so that when you put the 1/2, you put it in front of him only, okay? Because the first two terms, easy peasy, just you'll have antiderivative of 1 is x, antiderivative of 2e to the x is just 2e to the x. And then now you'll have 1/2 e to the u du. That's the e to the ax thing we talked about, I think, last week. And this is going to be 1/2 e to the u, which is 1/2 e to the x. Or 2x, sorry, 2x. Plus c. And there's your final answer for that last problem. Just foiling it out was the trick, if you will. It's not really a trick, but you want to know how to do the trick. Now, if that power had been like something crazy, like, I don't know, let's say instead of 2, what if it were 200? You wouldn't want to do this problem. That's when you would go get a computer system and say, screw it. Okay? You wouldn't even want to go there. You don't want to foil something out like that. That'd be nuts. Okay, any questions on that one? Everybody okay? You guys alive?
Yep.
Am I losing you? Here's the thing from teaching Calc 2 for a long time, since like 1996. What I notice is students who can't really get section 8.1, like it's a struggle, the rest of the semester is a nightmare because they don't know how to integrate. And it's just like, it's like not fun. The whole class is not fun for them. So you want to make sure that you get 8.1, which we're doing right now, completely okay with you. You know, now's your chance to ask questions. Or if you're too shy to ask questions in class, make sure you come to my office time, go to the tutoring that we have on campus. Anything you can to make sure that you support yourself, stay caught up. Okay, we're going to look at some hard problems now. I say hard because I'm not sure if they taught you this technique in Calc 1. If they did, great, but they may not have. And I'm going to make sure that you know it because believe me, it's going to be on an exam. Okay, so how do you deal with this? How do you deal with this special version of 1? Because right now, you can't use the log rule. It won't work. You could try, like, okay, u is the entire denominator. Fine, but then what's du? And the du isn't in there, so you get stuck. So that wouldn't work. So what you're going to do is you're going to take this thing and multiply it by a special version of 1. That's what I call this. But what's the special version of 1? Do you pull it out of thin air? No, it's an educated guess. What is it? Well, for this problem, because you have this exponential e to the 3x, you just, it's going to involve an exponential. You'll do e to the negative 3x. That's all, divided by itself. That's the special version of 1. So that makes this legal. You're not allowed to multiply an expression by just anything. You're only allowed to multiply it by 1 so that it stays the same. Now what you'll do is you'll multiply these two fractions together. So when you multiply the two numerators together, that's easy. And when you multiply the two denominators together, how about you distribute the e to the negative 3x over the sum? So when you multiply e to the negative 3x with 2e to the positive 3x, what do you get? What's e to the 3x times e to the negative 3x?
E
E to the 0.
Mm-hmm. But then you have the 2 there. So it's going to be 2 times 1, which is 2, plus, and then when you distribute the over the other term, you'll get e to the negative 3x. Okay, beautiful. Now, why is this so awesome? Because now this integral is integrable. You can do it. What rule of integration? The log rule. The log rule is going to work for us now. Why? Because if you let the denominator be the u, 2 plus e to the negative 3x, du is going to be negative 3 e to the negative 3x dx. Good news and bad news. Good news, e to the negative 3x dx is already in the integrand. The only thing that's missing that we need is a negative 3. Well, that's not a problem. You can always put in a constant multiple. That's legal. So I'm going to put in a negative 3, provided I multiply the front by the reciprocal. That's multiplying by a special version of 1. Okay. Well, let me do that in a half an hour, okay,
Yeah,
honey?
it's okay.
So then, this integral now, if I do the intermediate step, I've got negative 1/3 times the integral of 1 over u du, and that's going to give me negative 1/3 ln absolute value of u plus c, and then that's going to be negative 1/3 ln absolute value of, what do we have here, 2 plus e to the negative 3x plus c. And we're done with that problem. That was crazy. So let's recap. What was the trick, if you will? The trick was the strategy of you can't integrate this right now. It's not integrable. But if you first use this technique of multiplying by a special version of 1 and getting an equivalent integrand that does lend itself to a basic integration strategy, you're in luck. And we did. We got where the log rule made it happen, and then we were able to finish up the problem. Okay, let's take a quick yes/no poll. If you go to reactions and you can click on yes, no, do a yes if you've seen this technique before in your Calc 1 class by multiplying by a special version of 1. And if you never saw that in your Calc 1, click on the no button in the reactions. Okay, so I'm just an informal poll here, nothing big. Yes or no, go to reactions. Okay, we got 10 yeses, 8 nos, 11 yeses. Any more? Come on, people, vote. Just yes, no, no big deal. 12 yeses, 8 nos. Okay. All right, so a little bit more people have seen it than haven't, but I think it was worthwhile because the people that haven't seen it, you need to see it. Now you've seen it. Woohoo! Success! Yay! Cool beans. Any questions? Don't you think this is pretty cool? Where you do the special version 1 and it all works out? Is that not awesome or what? Come on, people. Who's with me? Nobody cares. Nobody
It's magic.
It's magic, yeah. Nobody cares. I mean, this is why teaching remote is like, I feel like I'm talking to a wall. Okay, before I do number 10, I'm going to do something that's not in your course reader, okay? This is multiplying by a special version of 1. And it's in your homework, so you better know how to do it. Come on. Let's take a look at it. And it's probably going to be on a quiz and exam. So it's not in your course reader, so copy this down, okay, people? You've got little blank pages there in your course reader for a reason, you know, so you can do extra stuff. So here's something extra for you, not in your course reader. Write it down, because I'm doing this for you for a favor. This is more for you, not for me. I already know how to integrate. I'm good. How about you? You're learning some advanced integration techniques, baby. So how the heck do you integrate that? Because that's a hot mess. Like, do not try to use the log rule. Forget arctan. Oh, God, no. This is yucky. But if you multiply it by a special version of 1, well, what's our special version of 1? Just hang in there. It's going to happen. It's like, And it turns out, because of the fact that if you did rewrite this guy as 1 over x, because that's what he is, your special version of 1 is going to be x over x. That's your special version of 1, okay? Now what? Multiply these two fractions together. Ooh, okay. Let's multiply the two numerators together to get the brand new numerator. Okay. And then multiply these two denominators together, and we'll distribute at the same time. All right, so we have x cubed times x, x to the 4th, plus 1 over x times x. Well, that reduces to just 1. Fabulous. Now what? Log rule will not work. Well, why not? I think it will. It's like, Yeah, Kelvin, you got it, arctan. Let me just go over why log rule won't work, because I know I have some people in the room who are like, yeah, well, I'm going to make it work. It's like, no, you won't. If you go log rule and you go, okay, well, the denominator, x to the fourth plus 1 will be my du, or my u rather, then my du is 4x cubed dx. But I got bad news for you. We don't have an x cubed. We only have an x in the numerator. So this is going to like, no way. So the trick is, this is actually the arctan rule. And I did a problem very similar to this during the first week of class. You probably forgot. But here's the trick. If I rewrite the denominator as a sum of squares, u is x squared. So du is 2x, and I got to put my dx here. Dx. Good news and bad news. There is an x dx there, but I need a 2. No problem. You're always allowed to put in a constant multiple, provided you multiply the front by the reciprocal. And then finally, the a, what's the a for my arctan rule?
1.
So now this is going to give me, I'll still have the 1/2 out in front. 1 over a is 1 over 1, which you don't even need to bother writing. Arctan of u over a, x squared over 1, which is just x squared. And then, of course, plus c. And so your final answer is just 1/2 arctan x squared plus c. So that one was kind of weird, but the special version of 1 was there to save the day. So it's helpful. So back to your usual regular programming, back to the course reader. Number 10. So I'm going to do number 10. And then I think I'll finish up and I'll save the rest of this stuff till next time. Okay. So before I do number 10, I want to say that when teaching remote is really a challenge, because I get students who apparently they don't like to follow direction from my lecture or my course reader or the book, and they end up doing things in very bizarre ways and they get a right answer. Okay, so I want to say that I put a problem like number 10 on a previous quiz or exam last semester, and I had a couple of students who did it in a very bizarre way. Like they used some sort of U sub that is, let's just say it's very non-conventional and non-traditional. And I didn't like it. And I'm like, where'd you learn that? 0 points. So I just want to give you a heads up that if you're going to go browsing around on the Google and find some weird thing on how to do this problem, which is not in alignment with the way we've gone over in class or the book or the lecture, that's great, but be prepared to not receive credit. Okay, so I'm just saying. That's how we roll. Okay, first up, I'm going to rewrite this as, just because it's going to be a little bit better for me, as 1 plus sine x for a reason. But there's this idea called Pythagorean conjugate. So let's do the hard work over here, the background, and then we'll get to do that problem. Because right now, this is not integrable. You cannot do this. There's no rule. The log rule won't work. Forget it. You're going to multiply it by a special version of 1, but what's the special version of 1? So first, you guys remember this trig identity that says, it's a beautiful trig identity, sine squared, ID, come on, Microsoft Surface Pro, don't let me down. Sine squared plus cos squared x equals 1. You guys have all seen that one, right? We all know that one?
Yes.
You've seen it. Okay, so what of it? Well, it turns out that it's going to be helpful in this problem. Okay, further, this idea of a Pythagorean conjugate, the Pythagorean conjugate of 1 plus sine x is 1 minus sine x. And who cares? Because when you multiply these together, something very nice happens. It's a difference of squares, a plus b times a minus b. And if you do FOIL this out, and you can FOIL it out on your own, you get the difference of squares. Well, so what? Well, it turns out that if you rewrite this trig identity that you just told me the difference of squares here, you can replace this with cos squared because it's the same. Well, how is that helpful? Well, that's just nice. So let me just go over another Pythagorean conjugate. Let's just say, what's the Pythagorean conjugate of 1 plus cos? Well, his Pythagorean conjugate is 1 minus cos. Okay, so you can kind of get this idea of Pythagorean conjugates. Okay, fine. Now back to the problem. So what of it? Well, you're going to multiply by a special version of 1 because right now this thing is not integrable. Ugh, it's a mess. So the special version of 1 is going to involve the Pythagorean conjugate for 1 plus sine x, which is 1 minus sine x, over itself, of course. Now what? Well, you still can't integrate this mess. You got to do a lot of cleanup. So let's do all the cleanup, and then eventually it's going to be integrable. So the cleanup is a little painful, and this is where students start skipping steps, and then they magically get the right answer, and then I magically take away all their credit. Yeah. So if you want all your points, do all the intermediate work in slow motion. So first up, let's multiply these two fractions numerators together. And that's easy because you're just going to get 1 minus sine x, because anytime you multiply by 1, you're good. Then the denominators, when you multiply those guys together, you'll get what I mentioned over here. You'll get 1 minus sine squared x, like that. But by the trig identity, this can be replaced with what?
Cosine squared x.
Mm-hmm. So you do that as your next step for your intermediate steps. And this is still not integrable. Don't go, okay, I'm good to go now. I'm going to integrate and just give my answer. Minus 50 million points for not showing work. Sorry, I'm not going to give it to you. You're going to use the split up trick. It's not really a trick, but you know, my Math 45 students thinks it is a trick. So you're going to split this up into 2 fractions. Okay. And you're going to even go 1 extra before you do anything. This is not integrable, but you're going to use another trig identity. What is the reciprocal of cosine equal to?
Secant.
Yeah. So the first integral, you're going to integrate sec squared, which is doable. And then the second term, which I'm just going to integrate separately, you're going to use the power rule. This looks like 1 over u squared du. Okay? So where u is cosine x, du is negative sine x dx. So I need the negative in there. So I can put 1 in, provided I put a negative in the front. But then I have 2 negatives out front here, so that's not really going to be a plus. The integral of sec squared, that's a regular formula you should have learned in Calc 1, that's tangent. Plus, this looks like 1 over u squared du right now. So if you remember, that's the same as the integral of u to the negative 2 du, which gives you u to the negative 1 divide out by negative 1, which is negative 1 over u. So this is tan x still, running out of room as usual, plus negative 1 over u plus c, but put your u back in. What was it?
Cosine.
So then you're going to have tan x, I'll do the minus instead of plus a negative, minus 1 over cos x plus c, but you're going to do one more trig identity for me. One last thing. What's 1 over cos?
Secant.
Secant, very good. So your last step is replace the 1 over cos with secant. So your final answer for this hellacious problem is tangent x minus secant x plus c. Woo! That was a handful. So to recap, special version of 1 comes into this situation on different occasions. And for this occasion, your special version of 1 involves something called the Pythagorean conjugate, which was useful because then when you multiplied your Pythagorean conjugates together, you were able to use a trig identity and replace, and then use the split up trick, and then integrate separately and finish up the problem. And yeah, that took some work. Like, oh my God, that was a nightmare. Ha, ha, ha. Okay.